Hi everyone, welcome back. In this video, we're going to take a look at a few other shapes that we see for polar equations, polar graphs. Specifically, we're going to pick up where we left off. We already learned about cardioids. Next up, we're learning about a new shape called a limacon. So we ended with cardioids last time, and I wrote this alternate form, r equals a plus or minus a cosine theta, or r equals a plus or minus a sine theta. One note about cardioids is they always pass through the pole also. So the end of that indentation is always going to be the pole or the origin. Another shape that we see is if we were to change these values so that they're not exactly the same. So the next shape we're looking at is called a limacon, and it's French, so sometimes you'll see this little accent underneath the C. Limacons are, well, let's take a look at the types of equations first. The equations are going to look similar to cardioids, except we have r equals a plus b cosine theta, or r equals a minus b cosine theta. So really similar. We have some number, and then we're adding or subtracting some number times cosine or sine. B times sine theta. Cosine and sine. However, a and b are different values in this case. Depending on what numbers we have for a and b, we're going to end up with different types of graphs. So, and these should be plus or minus. A plus or minus b cosine, a plus or minus b sine. So a plus b cosine theta, a minus b cosine theta. Either way, some number plus or minus some other number times cosine theta or times sine theta. Let's take a look at a couple of these equations on graphs, actually. Okay, so here we have Desmos. Here's a graph of a cardioid, which is what we looked at in our last video, passing through the pole. If we were to change these values, here we have 1 minus 1 sine theta. If we were to change these values to 1.5 minus 1 sine theta, we end up with a shape that looks like this outer shape. So it's kind of like a cardioid, but the indent doesn't go all the way in. So maybe a little bit more similar to like an apple. We have this indent, but it doesn't go all the way to the pole. And that's when we have the a value larger than the coefficient here, because this is just 1. So our a value is larger than b. If we were to switch that around and make the b value larger than a, so this is the shape we're looking at now, if we were to have 1 minus 2 sine theta, we end up with a more interesting shape, I think, which is this. So not only do we have this indent, but it actually keeps on going, and we have this little loop on the inside. And then it goes all the way back around. So it's almost like more of an indent to the point where we end up looping around on the inside. And that, again, is if our b value is greater than our a value. Okay, so looking back at our equations here, we have a few notes or takeaways that we can see from the graphs that we looked at. If a is greater than b, then we have a limacon with no inner loop, what they call it. So as we saw, it looks kind of like a little bit of an indent, but not a complete indent, and then a circle. And again, these being facing different directions, different orientations, depending on the sign used, plus or minus, and the trig function used, cosine or sine. If a is less than b, then we end up with a limacon with an inner loop. And as we saw, that looks like, and we have that circle shape. It almost looks like a cardioid, but it actually loops on the inside and then comes back out. So limacon with an inner loop if a is less than b. Okay, so if a and b are different values, we end up with a limacon, and then depending on which one is larger, we either have that inner loop or we just have a small indentation with no actual. Again, these, because they're similar to cardioids, we also see symmetry across the x-axis or the y-axis in the polar plane. Okay, let's take a look at another type of equation. This time we're looking at a rose. And it's called a rose because we end up with what looks like kind of like petals around our graph. The equation that we see for roses looks like this. So we have r equals a times cosine of some number n times theta. We also have r equals a times sine of n theta. And there are a few specifications or book puts. For example, a can't be 0 because then we just get r equals 0 in this case. And depending on what n is, we get different kinds of roses. So taking a look back at our graph. So for roses, we see, for example, here our first equation, we have r equals 4 times cosine of 3 theta. So for this equation, we see a rose with 3 petals. And that 3 is directly related to the 3 we have in front of theta here. So in this case, 3 means 3 petals, 3 theta, 3 petals. If we were to increase that number to 4, however, we get a very different rose. So as you can see, suddenly we end up with a lot more petals. And that's because if we have an even number, we actually have twice that number of petals. So here we have 4 in front of theta, and we end up with 1, 2, 3, 4, 5, 6, 7, 8 total petals. So if theta is odd, we end up with that number of petals. Or sorry, if n is odd, we end up with that number of petals. If n is even, then we end up with 2n number of petals. Okay, so a couple of quick notes. If n is odd, then we have n number of petals. If n is even, then we have 2n petals. The number of petals is determined by the number in front of theta in this case. All right, so our last shape that we're going to take a look at is called a lemniscate. Lemniscate, which is also called a propeller shape. In this case, our equations look like this. We have r squared equals a squared times sine of theta. We also have r squared equals times sine of 2 theta. I knew I was forgetting something. We also have r squared equals a squared times cosine of 2 theta. In this case, we have a propeller shape. So kind of similar to our rose, where if we have 2 in front of theta, we end up with 2 kind of like propellers or petals. In this case, even though it's even, we only end up with 2. Let's take a look at these equations on Desmos. And because we have a squared in front here, we know this is going to be a positive number in front. Okay, so Desmos doesn't like the r squared, so I did r equals square root of 4 sine 2 theta. And this actually gives us the plus or minus in this case. Here you can see we have this propeller shape, so kind of like 2 petals for a rose. And for all of these, the numbers are kind of related to the graphs. I don't know if you've noticed as we've gone through them, but here, for example, the 4 is related to the distance, the maximum distance we end up, which is 2 in this case. So that's why we have a squared in front of here. A is going to be the distance from the origin. So that is our last shape called a lemniscate, or a propeller shape. One last thing I forgot to mention was for the Limacon shape, these shapes, the name Limacon actually comes from Latin, and I think it means snail. So it's kind of similar to a snail, I guess, like kind of like a snail shell. But that's where the name Limacon comes from. Okay, so just a quick preview of the different types of polar graphs that we see, what their names are, and what all of their equations look like going through all of these different graphs.